So thank you for the introduction. So today I'm going to share work that I did with John Kececioglu about computing shortest hyperpaths for pathway inference in cellular reaction networks. So to go into background on what we are here talking about pathways and networks, a cell signaling pathway is this collection of reactions which starts at receptors typically and ends at target molecules. And then cell signaling networks contain the reactions from many of these annotated pathways kind of all together. So here is an example of one of these networks where each word corresponds to a protein or other molecule, and then each edge here corresponds to some kind of reaction taking place. So this is just kind of a simple example. So pathway inference then, the biological task that we address in this work, is given one of these cellular reaction databases, a set of available source compounds, and then a set of target molecules. We want to find a series of reactions that produces the targets from the sources. So infer one of these pathways. So why do we care about this task? So pathway inference can identify crosstalk and therapeutic targets. So crosstalk, I'll give kind of a cartoon. So say that you have an annotated pathway like this, and then a second annotated pathway that have both been found through experimental work. And we can now infer a pathway starting from the sources of the second pathway to the target of the first pathway, and show that in activating pathway 2, you might also activate pathway 1. So because these pathways are made of reactions, I'll just remind you what reactions look like. So reactions, you have the reactants on the left, products on the right, and importantly for this reaction to take place, all of the reactants need to be present, and when this reaction finally takes place, then all of the products will be produced. So what we want to do to infer these new pathways is to represent these reactions as edges in graphs. So I'll show you here based on this reaction from the previous slide. These are typically represented using ordinary graphs, where for each molecule in the reaction, you represent it by a vertex. And then you represent each reaction as this set of edges. This model, it doesn't accurately represent these reactions since you can traverse this top edge from A to C without ever reaching the other reactants. And when you reach C, you've not reached all of the products. So instead, what we're going to do is represent these reactions as hyperedges. So this single hyperedge represents the reaction that I've shown, where the reactants, or the things on the left, are in the tail of the vertex, the tail of the hyperedge, and the products are on the head. And importantly, this captures where you cannot traverse this hyperedge unless you've reached all of the tail vertices or unless all of the reactants are present. And upon traversing it, you now have reached all of the head vertices or in a sense, produced all the products of the reaction. So we can also generalize this notion of a path. So an ordinary path in a graph looks like this, where you have the source vertex, the sink vertex, and this sequence of edges reaching new vertices that connects S to T. So hyperpath now, you can have multiple hyperedges coming from the source, even if it's a shortest hyperpath. And then for any intermediate hyperedge, you need that its tail vertices need to all be covered by previous hyperedges in your hyperpath. And then finally, that the sink vertex or target is in the head of the final hyperedge in the hyperpath. So this is kind of an informal definition. I'll give a formal definition in a moment. But I wanted to first talk about the importance of these hypergraph models. So here I have the same instance of the problem, so the same source set, the same target, and the same reactions. But on the left, here's the hypergraph representation and the shortest hyperpath. And then on the right is the shortest path you'd find in an ordinary graph. And what you'll see is that on the left, because each hyperpath corresponds one-to-one with a reaction, you get this hyperpath that you find actually is biologically meaningful. These are actually reactions that take place in the cell, whereas the ordinary graph on the right, the shortest path, doesn't actually correspond to a biologically meaningful sequence of reactions that could actually occur. So now to go back and more formally define hyperpaths and superpaths. Here we first define an ST superpath, which you can think of as a set of an edge subset that connects S to T. So it's an ordered edge subset where the tail of the first hyperedge contains only the source vertex, and then for each subsequent hyperedge, its tail set is covered by the union of the source and the head of all the previous hyperedges, and then finally the sync T is in the head of the final hyperedge. So this defines a superpath, and then the definition of a hyperpath follows very easily, where an ST hyperpath is simply a minimal ST superpath, where here minimality means that if you take out any hyperedge in the hyperpath, it's no longer a hyperpath, or it's no longer a superpath. So now we can introduce the computational problem that we'll solve in this work. So given a hypergraph, a positive edge weight function, a source vertex S, a sync vertex T, we want to find an ST hyperpath of minimum total weight. So just some notes on the problem. It's an NP-complete problem, and we can reduce the multiple source, multiple sync problem to a single source, single sync problem, so that's what we'll focus on in the work. So these hyperpath models have been used in pathway inference, although traditionally ordinary graph models have been used since hyperpaths are NP-complete and very difficult to use, so there aren't many algorithms on them. So previous methods, Ritz and Morali in 2017, solved the shortest acyclic hyperpath problem. What is maybe unintuitive about shortest hyperpaths is that they actually can contain cycles. So here I've drawn a hypergraph where the only hyperpath from S to T is actually the entire hypergraph. So you have to use all the hyperedges, and the hyperedge that I've highlighted in red is actually causes a cycle because within its head set it has this vertex here on the left that is in the tail set of a previous hyperedge in the hyperpath. So this is an example where this previous method would not be able to find any hyperpath from S to T since they're all cyclic. Previously, me and my co-author have also published a general hyperpath heuristic. So this is now a heuristic that solves the general shortest hyperpath problem, or a heuristic for it, that now allows cycles, and I'll show you later that it's actually very accurate, but it's not an exact algorithm. So here we give the first exact algorithm for solving the general shortest hyperpath problem, and this is kind of an outline of what I'll talk about next, where we have a new graph theoretic characterization of hyperpaths in terms of cuts that's actually very clean, and this allows us to have an integer linear programming formulation of the problem, which unfortunately has exponentially many cuts, so we can't even feasibly write it down. But we also have a cutting plane algorithm that can quickly solve this full ILP in practice while operating only over a small subset of these cut constraints. This algorithm, while it has no runtime guarantee, solves real-world instances very fast in practice. So it has a median runtime under 10 seconds on these real biological databases. And we call this tool Munin, and I'll show this URL at the end as well. But we have implemented this in a tool and have all the data sets available. So first I want to talk about our graph theoretic characterization of hyperpaths in terms of cuts. So first I have to define what a cut is. So an ST cut is this bipartition of the vertices, where S is on one side, T is on the other, and we commonly just refer to the S side of the cut, C. So then the definition of crossing a cut then is hyperedge E crosses a cut if all of its tail vertices are on one side, on the S side, and you have at least one of its vertices on the T side. So here's a picture of this. So if you have S and T and this hyperedge E, and you have this cut C, we would say that hyperedge E does cross cut C since all of its tail vertices, A through B, are on the S side, and one of its head vertices, Y, is on the T side. So in the paper, we proved this theorem. This is the characterization theorem that an edge set F is an ST superpath if and only if F crosses every ST cut. So this is a simple theorem, and it enables us to model superpaths by cut constraints in a fairly clean and integer linear program. So for this integer linear program, we have a binary variable, x sub e, for each hyperedge E, where 1 indicates inclusion in the shortest hyperpath, 0 indicates that it's not in the shortest hyperpath. And then our constraint set, so the constraints, we have 1 for every ST cut, which simply looks at all of the hyperedges crossing that cut and ensures that at least one of the indicator variables is active. And then our objective function seeks to minimize the total weight of these chosen hyperedges. So the constraints by the theorem ensure that this is an ST superpath since it crosses every ST cut. And then the objective function ensures it's minimal, and because it's minimal, it's now a shortest ST hyperpath. But as I said earlier, this unfortunately has exponentially many cuts, so we can't even feasibly write it down, let alone solve it. So we compare our method to these other state-of-the-art methods that I introduced earlier. So acyc MILP is from Ritz et al., and it's an exact algorithm for acyclic shortest hyperpaths. And Huygen is the hyperpath heuristic that we developed earlier, and then Munin is this exact algorithm that we developed in this work. So acyclic MILP is actually suboptimal on many of the instances from these two databases, since for these instances, they only have cyclic hyperpaths. So these are instances where they return no hyperpath even though one exists. Huygen is actually heuristic, but it's surprisingly accurate. There's only a small number of instances where it's suboptimal. And then Munin, since it's an exact algorithm, is obviously suboptimal on none of these instances. And the question then is, if it's an exact algorithm to an NP-complete problem, how fast is it running in practice? On these 7,600 instances, so on many instances of the problem, we found that the median runtime is 9 seconds, and the maximum running time is also fast, that it's under 30 minutes. So now I just want to show one example of one of these hyperpaths that we find. Here it is. I show the sources that we actually use on the top. And then it's this hyperpath to this phosphorylated p53 tetramer, which is down here on the bottom right. And I've highlighted the hyperedge in red, E7, since it creates a cycle. So this is actually a cyclic hyperpath that is shortest. And so this is an example that the previous state-of-the-art would not be able to find. So in conclusion, I've presented the first exact algorithm for shortest hyperpaths. While there's no guarantee on the running time, it finds shortest hyperpaths remarkably fast in practice. So I'd like to acknowledge T.M. Morali and Anna Ritz for introducing us to the shortest hyperpath problem, funding from the NSF, and then I put the tool URL on here, and then also, for those who missed the very beginning of the talk, my name and the title of the talk. And now I'm ready for any questions.